Welcome to Control Systems N6. Today's presentation is going to be on Laplace transforms. This is the first module in your syllabus. As a matter of fact, in most of your exams, you will have one question that comes from this module. And so it's really important for you to pay attention. And if you do, by the end of my presentation, you should be able to tackle any question that you may get in your exam. And also, before I begin, I just want to remind you to subscribe to this channel and please like the video, because when you do that, it encourages me to continue to produce content of this nature. Let's begin. First, I want to begin by introducing to you why Laplace transforms are important. Especially for you who is doing control systems N6, you need to understand that Laplace transforms are very, very important for you to understand. And the first reason I will give you is because Laplace transforms make it easy to solve differential equations. If you are doing maths N6, you will do differential equations, and maybe you've already done them, and if you have, then you know how difficult it can be to solve a differential equation. But the beautiful thing with Laplace transforms is that they make it easy for us to solve many of the differential equations, because all we do is that we take that differential equation and then we take it to the Laplace domain, or we find the Laplace transform of that equation, and you will see that the differential equation in the Laplace domain will generally just look like a simple algebraic equation. And because it looks like a simple algebraic equation, it becomes easy to solve. But if you had to solve it without transforming it, then the work can be so difficult and so tedious. And that is why Laplace transforms are very much used in solving differential equations. But in control systems N6, we don't just need Laplace transforms for us to be able to solve differential equations, but we also need them for signal processing. And what I mean by that is that in control systems, generally you will be dealing with different kinds of systems, and it is often possible to represent a system by a transfer function. And so once you have the transfer function of the system, it is then possible for you to describe a relationship between the input to the system and the output of the system. And so to be able to do all of that, you will need Laplace transforms. And so these are the two main reasons for somebody who is doing control systems N6. These are the two main reasons you need Laplace transforms. And so now that I've told you why you need Laplace transforms, let us look at what exactly is a Laplace transform. And for that, I will begin by introducing to you the two domains that are going to be of use when we're dealing with control systems. Okay, so the first one is the time domain, which is generally the domain from which we go from, okay, the time domain. And then after the time domain, you have the Laplace domain. And the Laplace domain is the domain to which we are going to. Okay, so basically what I'm trying to say is that generally we will transform something from the time domain to the Laplace domain. But of course, you can get a situation where you are given something in the Laplace domain and you have to revert, okay, so go back to the time domain. But in most cases, the initial place you start from is the time domain. And then using Laplace transforms, you can transform the function that you have in the time domain to have an expression of it in the Laplace domain. And so let's say we have a function ft in the time domain. And as you can see, this is a function of time. T here represents time. And so this is a function of time, ft. And so now we need to transform it to the Laplace domain. Okay, so we need to find the Laplace transform of this function ft. And so what is that going to be? The Laplace transform of this function ft is the function that you see here, fs. The first thing I want you to notice here is that when we are in the time domain, generally we will use a small letter to describe the function, but in the Laplace domain, we use a capital letter to describe the function, okay? So you can see here you have small f, but here you have capital F. And also in the time domain, your function is a function of time. That is why you see t. But in the Laplace domain, this function, after it has been transformed, becomes a function of s, okay? And fs, capital Fs here, is pretty much the Laplace transform of this function ft. And the way to write that, to say that it is the Laplace transform of ft, you just write capital L and in brackets you put ft. This means that fs is the Laplace transform of this function ft. And to calculate it, what you need to do is to calculate the integral going from 0 to infinity of e to the minus st multiplied by the function ft for which you're trying to find the Laplace transform, okay? And that will be dt because this ft is a function of time. So we are integrating with respect to time, okay? And so this is basically what the Laplace transform is. So you have a function in the time domain ft, and you have to find its Laplace transform in the Laplace domain, of course, and that will just be therefore capital Fs, which is the Laplace transform of ft. And to calculate it, you need to take the integral from 0 to infinity of e to the minus st multiplied by ft being the function for which we're trying to get the transform, the Laplace transform. And of course, we integrate with respect to time, to t, okay? Very important for you to understand that. And now, because the time domain, we use the letter t to refer to time, the time domain, therefore, is also called the t domain, okay? And in the Laplace domain, we use the letter s, okay? F is a function of s, therefore the Laplace domain is also referred to as the s domain. So sometimes you may find someone saying time domain, or they may just say the t domain. And another may say Laplace domain or just say s domain. These are just the same expressions, okay? They mean the same thing, different expressions, but they mean the same thing, okay? So the time domain is the t domain, the Laplace domain is the s domain. And the reason we call the Laplace domain the s domain is because everything will be as a function of of s, okay? So I repeat, the time domain is the t domain, the Laplace domain is the s domain, and the reason we call the Laplace domain the s domain is because every function in the Laplace domain will be a function of s, okay? I hope I am making myself clear. And so to explain further, we're gonna do a little example. Now, let's say you have a function here, ft, which is equal to e to the minus at. A is a constant, and t, of course, is the variable because we are in the time domain, so t is actually the variable of time, okay? So you have this function ft, which is equal to e to raised to the power of minus at. I repeat, a is a constant. Now, if we have to find the Laplace transform of this function, what are we going to do? Of course, we're gonna use this equation here, okay? So we will need to calculate the integral from 0 to infinity of e to the minus st multiplied by ft, except that in this example, the value of ft will be this because we know what ft is equal to. So you will replace this ft by that. And so that's what we're going to do. And so we know that fs is equal to this integral, but you can see that ft here has been replaced by the value for ft in this example, which is e to the minus at. A is a constant, I repeat. And so now that you have to calculate this integral, okay, it's going to be easier for you to first notice that you have e raised to the power of minus st multiplied again by e raised to the power of minus at. So you can just write therefore that this is equal to e raised to the power of this plus that. Okay, so if you add this to that, what you get is this here. Okay, what I did, I just took the minus sign outside of the bracket and I wrote it like that. But this here is pretty much minus st plus minus 80. So minus st minus 80. Okay, because when you have something like this, e raised to a power multiplied by e raised to another power, you can just sum the powers. Okay, you know that from maths, and that is exactly what I did here. So finding the Laplace transform of this is essentially solving this integral here. And of course, we are solving this between 0 and infinity. And so if you remember your integration, the integral of this term here is what you will get here. Okay, it's quite easy to see. And so if you are struggling with derivation and integration, I am not gonna get into that here because this is a control systems course. Okay, you need to go and revise your maths course. But here I am just assuming that you know the basics of integration and derivation, and I am going to build from that. And so if you integrate this here, this is what you will get. This is what you will get. And once you have this, now you need to remember that this uh, integral is between 0 and infinity. Okay, so we are not yet done. We need now to find the value of this integral if we're integrating from 0 to infinity. Okay, so the lower limit is 0, and of course the higher limit will be infinity. And so if you try and find what this will give you between 0 and infinity, you know how we do that. So first you need to find the value for this when t is infinity. Okay, and so if you do that carefully, you will find that this will give you 0 if t is infinity. The reason for that is because e to the power of minus s plus a multiplied by t. If you put t as infinity, then you will have e to the power of minus infinity, and that gives you 0. Okay, and so therefore when we replace t by infinity here, what we will get, of course, is 0. And then we need to do minus, and then we take again this here, and now this time we replace t by 0. If you replace t by 0, this becomes e to the power of 0, which is 1. And so you will have minus this. Okay, and so if you do that carefully, what you will end up with, if you are integrating this between 0 and infinity, the answer you should arrive at is that 1 over s plus a. Okay, very, very important. Again, I say if you're struggling to understand what I am doing here with integration, I will advise you to revisit your math course and make sure that you understand that, and then you can come and try to do this, and you will see that the right answer that you will get is actually 1 over s plus a. This is actually a very simple function to integrate. Okay, there is nothing difficult. And then you need to, once you have found what the integral is, you then need to evaluate it between these two limits. Okay, between 0 and infinity. And so if you do that, then what you get is that the transfer function of this is actually 1 over s plus a. And as you can see, sorry, the Laplace transform. I said the transfer function, but what I meant is the Laplace transform, okay? The Laplace transform of this function here is actually that, okay? And as you can see, this function is all a function of s. You don't see any t here. That is why we refer to this as the S domain, because every function you have is a function of S, okay? Very, very important. And so this is pretty much what the Laplace transform is. So if you are given a function ft, finding the Laplace transform of that function is just integrating between 0 and infinity the product of e to the minus st by ft being the function for which you're trying to find the Laplace transform. And of course, you need to integrate with respect to time, okay? Because as I said, in control systems N6, generally we deal with the time domain and the S domain or the Laplace domain, okay? But of course, in maths, here you could have x, fx, okay? It's the same thing. If you have fx, then here you will have fx and you will integrate with respect to x, so it will be dx. But generally, when we're dealing with control systems, it's the time domain, so generally ft, and in the Laplace domain, then this is what you will get, and of course it's going to be a function of s. Very, very important. And so you will find in your exams that they will give you a table of Laplace transforms. And the reason they do that is because in control systems N6, we're not really trying to see if you can integrate and find what the Laplace transform of a function is. Okay, that's not really what we want to do. This is control systems, it's not maths. Okay, and so generally in your exam you will get this table, and this table has different Laplace transforms for different functions, okay, in the time domain. Okay, and so it's going to be up to you to be able to look at this table and to identify exactly which function that you have in your question is corresponding to in the table, and then from there you can then come and read what will be the Laplace transform for that particular function. Okay, and so really, really important to be able to do that. Otherwise, if you can't localize that here, then you're gonna be forced to integrate, and integration can be quite difficult to do for some of these functions. And that is why I am saying to you, it is much better for you to be able to see the function that you have in your question and see what looks like that function in the table here, okay? And then you will be able then to find the equivalent Laplace transform. And sometimes they can also give you a function that is in the S domain, and then they ask you to find what it is in the time domain, okay? And so again, the function that you will get in your question will look like one of the functions here in the table, but you will need to be wise enough to be able to see which one. And then from there, you will then be able to see what is the equivalent function in the time domain. Okay, so very, very important for you to familiarize yourself with this table of Laplace transforms. This is the exact table that you get in your exam. Okay, it's got a few mistakes here and there, but the more you use it, the more you will become familiar with the mistakes and you will correct them when you see them even in your exam. Okay, but this table that you see here is the table of Laplace transforms that you will get in your exam. Okay, as an appendix, you will have this table of Laplace transforms. Okay, very important for you to be familiar with it and also to be able to see in that table and find which function is actually very similar to the one that you have in the question. And then you need to be able to apply your knowledge of this table to determine what the Laplace transform is going to be if the function that you are given is a function in the time domain, or what the function in the time domain is going to be if the function that you are given in your question is in the S domain. Okay, we're going to do some examples of that and it's going to be very clear. But before we go to that, what I want to show you first, before examples, is the Laplace transform of derivatives. Okay, it's really important for you to also be able to calculate the Laplace transform of a derivative. Okay, you're gonna need to be able to do that for control systems, and so this is what I am going to introduce to you now. So again, we know that we have the time domain and we have the Laplace domain, and the time domain, as I said earlier, may also be referred to as the t domain, and the Laplace domain is referred to also as the S domain. The reason being that in the time domain, the variable is time, so t, and in the Laplace domain, every function is a function of S, hence we call it the S domain. Okay, very important. Now, of course, in the time domain, the function that you have will be small ft, but in the Laplace domain, the Laplace transform of that function is capital F S, okay, because it is a function of S. And notice that in the Laplace domain, we use capital letters for the functions, but in the time domain, we tend to use small letters, okay? So ft, when you transform it to the Laplace domain, the function that you get is Fs, which is just the Laplace transform of ft. And as I said to you earlier, it's the integral from 0 to infinity of e to the power of minus st multiplied by ft. And we take that integral with respect to time, so dt, okay? We just saw that. Now, the first derivative of ft is f prime t, okay? You are familiar with this way of writing the derivative from your maths course, okay? And so the first derivative of f with respect to time is df over dt, okay? So that's the first derivative. Now, if we want to take the Laplace transform of the first derivative, what are we going to get? Okay, so if we go in the Laplace domain, the Laplace transform L like that of f prime of t, okay? This here is the Laplace transform of f prime, okay? F prime is the first derivative of f with respect to time. So the Laplace transform of this, what is that equal to? It's simply equal to this here, okay? So it's equal to S multiplied by Fs. What is Fs? Fs is the Laplace transform of Ft, okay? So it's going to be S multiplied by Fs minus F of 0, okay? So what is F of 0? F of 0 is the value that you get for Ft when t is equal to 0, okay? So this is pretty much what f of 0 is. It's the value you will get for ft if time is equal to 0. And so I repeat, the Laplace transform of the first derivative of f with respect to time is equal to s fs, fs here being the Laplace transform of ft, okay, minus f of 0. F of 0 is what you will get if t is equal to 0 in this function ft. Okay, so that is what the Laplace transform of the first derivative is. So now, what will be the Laplace transform of the second derivative of f? F double prime t, or this here, the second derivative of f with respect to time, what will be the Laplace transform of that? Well, the Laplace transform of the second derivative of f with respect to time is equal to this, okay? And you can see it's s squared fs minus s multiplied by f of 0. I explained what f of 0 is, and then minus f prime of 0. So what is f prime of 0? F prime of 0 is pretty much what you will get if you replaced t by 0 in the first derivative of f. So once you've calculated the first derivative of f here, you may get an expression with t. So if you make that t equal to 0, what you get is what we call f prime of 0. Okay? And so the Laplace transform of the second derivative is therefore given by this. The Laplace transform of the third derivative, this is the third derivative. If we're looking for the Laplace transform of the third derivative, what we get is that, okay? And of course, you can see it's s cubed multiplied by fs minus s squared multiplied by f of 0 minus s multiplied by f prime of 0 and then minus f double prime of 0. F double prime is just the second derivative of f with respect to t. And now you need to replace t in that expression by 0. Okay, that is f double prime of 0. Okay, very, very important. And so this is pretty much the Laplace transform of derivatives that you will need to know for your control systems N6. I'm not going to go to the fourth and fifth derivative because as far as your control systems N6 is concerned, it's less likely that you will ever go beyond the third derivative. In fact, in most questions, you stop at the second derivative, okay? And so it's important for you to know how to find the Laplace transform of derivatives. And this is pretty much the equations that you need to know, okay? Fs, I repeat, is the Laplace transform of ft. F of 0 here is the value you get when you replace time by when you replace t by 0 or when time is equal to 0. Okay, so f of 0 is what you will get when you replace time by 0 or t by 0 in the expression for ft. That's f of 0. F prime of 0 is what you will get if you replace t by 0 in the expression for f prime t. Okay, the first derivative of f with respect to t. F double prime of 0 is what you will get if you replace t by 0 in the second derivative of f with respect to t. Okay, very, very important. And so now that we have it like that, now that we know how to do the Laplace transform of derivatives, and we also understand what Laplace transforms are, and we are also familiar with the table of Laplace transforms, we are well able to then tackle questions from this module. And so the first example that we're going to look at is this one. It's taken from one of your past papers. As I said to you, generally in your exam, you will have one question that comes from this module. And so this is what they had for that particular exam. And so for question 6.1, they ask you to express the given function in terms of the equivalent Laplace transformation. Okay, so you have this function here, and as you can see, this function is made of derivatives. Okay, so we need to find the Laplace transform of this whole thing. We will find the Laplace transform of the term on the right, and this, of course, must be equal to the Laplace transform of the term on the left. Okay, and so you can see here we're gonna have to do the Laplace transform of derivatives, which we just saw. Okay, and then for question 6.2, you need to use Laplace transforms to convert the following function to the S domain. Okay, so you have this function here, which is in the T domain, and now you need to transform it to the S domain. Okay, And of course, we are going to use tables. You're not gonna just work out an integral. I said to you, this is not a math course, so generally for control systems, you will not be expected to work out integrals, but rather what you will be expected to do is to be able to look at the table and find a function that is equivalent to this one and what its Laplace transform looks like. Okay, so you need to look at this function that you have carefully and then look at the table carefully and see which one is like this one. And then once you have found it, then from the table you will also be able to see what the Laplace transform of that function is supposed to look like. Okay, so that's what you will be expected to do. You don't need to go and do the integral of this whole thing. This is not a maths course, this is a control systems course. For question 6.3, now they say to you, using Laplace transforms, convert the following function to the t domain. So now for question 6.3, they've given you functions in the S domain, and now they want you to convert back to the time domain. And so again, here you will have to look at the table and see among the functions in the S domain that you have, which ones look like this. And then you will read the corresponding values for the t domain. Okay, so that's pretty much what you will have to do for this question. And so let us begin with question 6.1. So first, what you need to understand is that y that you see here is a function of time. Okay, y is a function of time, it's yt. And even the x that you see here is also a function of time, and this is xt. Okay, very important to understand that both y and x in this here are functions of time. And this question should have told you that, okay? To be thorough with the question, the person who wrote this question should have taken the time to also state that y and t are that y and x are functions of time. Okay, they should have said that clearly. And also to be able to take the Laplace of something like that, they also need to tell you what are the initial conditions. Okay, they need to tell you what is y of 0, what is y prime of 0, what is y double prime of 0. Okay, and also they need to tell you what is x of 0, x prime of 0. Okay, they need to tell you that before you can take the Laplace transforms here. The reason for that is because we're doing Laplace transforms of derivatives. Okay, so you need to know those initial conditions. But since in this case we haven't been told anything about the initial conditions, what we're going to assume is that all the initial conditions are 0. What I mean by that is that y of 0 is equal to y prime of 0, and all of that is equal to 0. And also x of 0 is equal to 0. Okay, and so what is y of 0? Y of 0 is what you will get when you replace t by 0 in the function yt. Okay, yt is equal to something. Okay, we don't know what it's equal to, but what you will get by replacing t by 0 in that function is what y of 0 is. But in this case, we haven't been told what y of 0 is or what y prime of 0 is. Therefore, we are just going to assume that both are equal to 0. Same thing with x. We haven't been told anything about x, so we will also assume that x of 0 is equal to 0. Now, once we've made these assumptions, we can now come here and take the Laplace transforms. Okay, here you have an equality. Okay, so the Laplace transform of what you have on the right must be equal to the Laplace transform of what you have on the left. Okay, so what you have on the left, the Laplace transform of what you have on the left must be equal to the Laplace transform of what you have on the right. Okay, So that is exactly what I did here. So I took the Laplace transform of this expression that I have on the left must be equal to the Laplace transform of the expression that I have on the right. Okay, because we have an equality. And now, once we have it like that, now what you need to know is that the Laplace transform of a sum is equal to the sum of Laplace transforms. So what I mean by that is that this can be rewritten like this, okay? So the Laplace transform of this whole thing is equal to the Laplace transform of that plus the Laplace transform of that and so on. Okay, so we write it like that. Here we have a negative sign because it's minus 27y. So it will be minus the Laplace transform of 27y. And all of that must be equal to the Laplace transform of 27x. Okay, very important. Now, the second thing I need to show you also is that when you have a product like that, okay, 3 multiplied by the second derivative of y with respect to t, because we multiply 3 by that, you might as well take 3 outside and then look for the Laplace transform of the second derivative only, okay? And you can do the same thing here, the same thing everywhere. And so this can be rewritten like that. So it's 3 times the Laplace transform of the second derivative of y with respect to time plus 9 times the Laplace transform of the first derivative of y with respect to time minus 27 multiplied by the Laplace transform of y, and this will be equal to 27 multiplied by the Laplace transform of x. And again, although I wrote y here, just like that y, but really this y is yt, okay? It is a function of time, so it's yt. You could have written Laplace transform of yt, and here you could have written Laplace transform of xt. But because they wrote the question like that, I just decided to stick to the way they wrote it here. That's why I said Laplace transform of y, and on that side I said Laplace transform of x. Okay, you can see that here. Okay, very important. And so once you have this, now you need to remember how to find the Laplace transform of derivatives. Okay, and I will remind you here in blue what is the Laplace transform of the first derivative of a function, and also what is the Laplace transform of the second derivative of a function. So the Laplace transform of a second derivative of a function, like in this case y, because it's the second derivative of y. Okay, so it's going to be therefore s f of s. In this case, it's going to be y of s because our function is not f but yt. Okay, so it's going to be s squared y of s minus s multiplied by y of 0. Y of 0 is 0, okay, and then minus y prime of 0, and that we also take as 0 because in this question they did not give us initial conditions, and therefore we are just assuming that they are all 0. Okay, so since this and this are both equal to 0, therefore the Laplace transform of the second derivative of y will just be equal to s squared multiplied by ys. Okay, so that is what we will get here. And here for the first derivative, it's just going to be s multiplied by ys. Okay, it's not f, the function, but y. So that's why it's ys here. And minus 27 Laplace transform of yt. Okay, what is the Laplace transform of yt? It's ys, capital ys, because in the Laplace domain we use capitals and not small letters. Okay, so this here Laplace transform of yt is just capital ys, and here Laplace transform of xt is capital xs. Okay, because we are in the s domain once we've taken the Laplace transforms. And so if you do that correctly, this is what you should get, okay? 3s squared ys plus 9s ys minus 27 ys. This ys here is just the Laplace transform of yt or y. Remember I said y is actually yt because it's a function of time, same as x, it's xt, it's a function of time. I'm just not writing yt here and xt there because this is the way they wrote them in the question. But both y and x are functions of time. And so if you do it correctly, you will have this, and all of that will be equal to 27xs. And you notice it's capital X and it's capital Y because we are in the S domain, in the Laplace domain. Once you take the transforms, the functions take capital letters. And so L of X is the Laplace transform of xt, so it's xs. And so once you have it like this, you can see on the left side of the equal sign here, you have ys everywhere, so you can take it out of the bracket like that, okay? And this will be equal to 27xs. And now what we can do, we can then take the functions of s and put them on the left side of the equal sign and every other thing on the right side of the equal sign. And so if you do that, this is what you will get. Ys over xs must be equal to this. And this is not the end of it, because if you look carefully, you will see that you can divide both the numerator and denominator by 3. Okay, so you need to be thorough. Do not just leave your answer like this, but rather simplify it, because there is a possibility to simplify it. So dividing the numerator and denominator by 3 will lead you to this answer here. And so this is pretty much as far as you can go as far as taking the Laplace transform of this expression is concerned. Okay, so your answer will be ys over xs is equal to this. Okay, that's pretty much all you needed to know. So if you understand that to do the Laplace of derivatives, then this here will be really easy. Now, question 6.2, we are given this function. This function is given in the time domain, okay? And so we need to find its expression in the S domain. So we need to find the Laplace transform of this. Again, you do not need to do the full integration. This is not a math course. You are to use the table, okay? You have to use the table. And so to find f of s, we need to find the Laplace transform of that expression, okay? The Laplace transform of this whole expression here. That is f of s that we're trying to find. Now, if you look in the table that I showed you earlier, okay, which is the table that you will find also in your exam, you will see that if you look in row 13b, okay, so this is row 13b, you will find that you have on this side a function in the time domain, and on this side you have the equivalent of that function in the Laplace domain, okay? So you have the Laplace transform of this function, it is this here. And so if you look at this, this row 13b in the table, you can see that this function that you have here in the time domain closely resembles the one that you see here, okay? And you can then establish what is a in this function, and also what is small a and what is capital A, okay? You can establish that. And so if you look at this function carefully, you will see that small a here is 16, okay? And therefore, a squared is 256, because if you do 16 squared, that's 256. And capital A that you see there is 24, okay? And so this is what you can do by inspection, okay? That's how you use the table of Laplace transforms, okay? You use it by inspection. So you look at the function that you are given in your question, and you carefully look at the table, and you will see that there is a function in the table that closely resembles the one that you have in your question. And so you can then use that to establish what the Laplace transform is going to be. And so this function in the time domain that we were given in this question looks like this one here that you have in the table. But of course, in the table, they did generalize the function, because they've just left letters, okay, capital A and small a, so that any function that you will have looking like this, you will just now find for yourself what the small a is and what the capital A is. In this case, if you look at this carefully, you will see that the small a is 16 and the capital A is 24. And if you check, 256 that you see here is a squared, is 16 squared. Okay, so once you have this like that, you know what capital A is and what small a is. Now you know that that the Laplace transform is actually this function here. Okay, so it's capital A over s squared multiplied by s plus a. Okay, but in this case, our capital A is 24, our small a is 16. So our Fs will therefore be equal to 24 capital A divided by s squared multiplied by s plus small a. Our small a is 16, so you put 16 there. And if you do that, that's it. You found the Laplace transform of this function, okay? You found it. This is what it is. And you can see that it was pretty much a two-line exercise because we were able to make good use of the table. So I will advise you to familiarize yourself with that table because you will use it a lot in control systems N6. Okay, if you look at row 13b, okay, this is the row where we find a function that closely resembles the one that we have here. Very good. Now, question 6.3.1. This time we are given a function in the S domain and we have to find the equivalent in the time domain. So we're doing the reverse exercise. But again, you don't need to struggle with maths, okay? This is control systems. You are just going to look at the table and see if you can find a function in the S domain that looks closely, that looks something like this, okay, that closely resembles this. And once you have found that function, then you will just read in the table what is the equivalent function in the T domain, and then you will adapt it by, of course, finding what each of the variables stand for, exactly like we just did. Okay, so in this case, we have our Fs, which is this. So if you look in the table, of course, we're trying to find Ft, okay? So if you look in the table, you will see that row 9b, okay? If you look at row 9b in the table, you will see that you have a function in the S domain that looks like this, okay? A over S plus A multiplied by S plus B. Now, at first glance, you may say, oh, but this doesn't look like that. But the truth is, if you make A equal to 0, then of course what will remain here is S, okay? And S plus B, if you want it to be S minus 6, then B must be minus 6. And A therefore is 18, okay? So if you look at it carefully, this is what you have. A must be 18 here, and small a, okay, capital A is 18, small a must be 0 so that we remain with S, and B here must be minus 6 because it's S plus B, so B must be minus 6 so that we have S minus 6. And so once you have written it like that and you have identified what these constants are, then immediately you can now come here and write the expression for it in the time domain, okay? A is 18, B minus A will be minus 6 minus 0, and then multiplied by that, okay? So if we do that correctly, this is what we will have, okay? Ft will be, because what you have in this on this side is the function in the time domain. What you have here is the function in the S domain, okay, the Laplace domain. Okay, in this case, we were given the function in the Laplace domain. We want to find the function in the time domain. So first, we establish what these constants are here. And once we have them like that, we can come here and plug in the values and get what the function will be in the time domain. And so in this case, A is 18, B is minus 6, minus 6 minus A is 0, so it's minus 6 minus 0. all multiplied by e to the minus at. Okay, so e to the power of minus aa0 minus 0t minus e to the power of minus bt. Okay, b is minus 6, so if you do minus b, it's minus minus 6, so it's 6 multiplied by t, okay, in the exponent here. And so this is what you should get if you do it correctly. And so e to the power of 0 is 1, okay? And so 18 divided by minus 6 is minus 3, and so we can simplify it further. And so you will get minus 3 multiplied by 1, e to the power of 0 is 1, minus e to the power of 60. And you close the bracket. And so this is what you get for ft. And as you can see again, if you can read your table carefully, and if you understand that to use it, doing these kinds of exercises is really easy and really straightforward. And in your exam, you can quickly secure 10 to 12 marks just because you can use your table correctly. Let's go to question 6.3.2. And so again, we're trying to find ft. We are given fs. And now you again need to go and look in the table, okay? And so I will advise you, even while you're watching this video, to have that table next to you and to check if you can see that to check if you can find these things, okay? And if you can find these rows that I'm pointing out to you, okay? But just make sure and practice and make sure that you understand how to use the table, how to recognize the various functions in the table, okay? And again, once you've recognized the functions, then your next step is to actually assign values to the constants, because you can see here in the table, you just have constants, you don't have numbers. And so you need to assign values to the constants for you to then be able to work this table. Okay, very important. So in this case, we have this function in the S domain, and now we're trying to find what the equivalent will be in the time domain. And again, if you look at the table, you will see that there is a place where you have a function like that in the S domain. And that is in row 11, okay? In row 11, you can see here, if you look at this, you will see that this closely resembles that, okay? And so this here is the S domain, and so the function that corresponds to that in the T domain is this function here, okay? And so the only thing that we need to establish here is A. What is the value of capital A? So if you look at this here, it's quite easy to see that capital A is actually 12, okay? And so we will come here now where we have the function in the time domain, and we will just replace this A by 12, because everything else is not something that you need to replace, okay? Everything else pretty much remains like that. And so if we do that, then ft becomes this. Okay, that is what it is. It's as simple as that. That's all you had to do for this question. Now, let us look at another example, which is again coming from another question paper. And as you can see, for question 6.1, you have to convert the Laplace transform functions below to a function of s. Okay? So here they've given you functions in the time domain, and you have to change them to the S domain, basically. And then for the second part of the question, you now do the reverse. You are given a function in the S domain or the Laplace domain, and you need to take it back to the time domain. And so let's do question 6.1.1. Okay, we have this function ft, which is equal to 15 cos 135t. So now you need to go to the table and see if you can find a function that closely resembles this one. And so if you go there, you will see that in row 7, if you look at the function that you have in the time domain in row 7, is A, capital A cos omega t. Okay, and if you look carefully, you will see that the value for A that you have is 15, and the value for omega that you have is 135. Okay, I hope you can see that. If you look at this function, closely resembles this one, and the value for capital A is 15, and the value for omega, which is here, is 135. And so the function for it that you need to find in the Laplace domain is this function here. Now, what I want to point out to you is that in your table, what you see written in the numerator here is A, and then as a subscript, they write S, but this is a typo. Okay, so if you have that table with you, you need to correct that A subscript S. It's actually supposed to be capital A multiplied by S, okay, in the numerator. See how it is looking? This is wrong, okay? It's not A subscript S. It's A multiplied by S. And so I'm going to make that correction now. So it's supposed to actually be like that, okay? So this is A multiplied by S. So you need to make that correction in your table as well. That is why I said you need to use that table already while you're preparing, so that you become familiar with the small mistakes that are in the table. If you don't start working already with that table now, when the exam comes, you may wonder what's going on here. Okay, so familiarize yourself with that table and with some of the mistakes that are there, just so that when you get to the exam, you know that this here is a small mistake and you can correct it for yourself. Okay, so now in the Laplace domain, our function is this function here. Okay, very, very important. And so what is A? Again, A is 15, that omega is 135. And so we can just quickly write Fs, and it's going to be 15s in the numerator because A is 15 divided by s squared. Omega is 135, so since we have omega squared here, so it's going to be 135 squared. And of course, this here, you can write what the value for that is. Okay, so we can go a step further and say that Fs is actually equal to this. Okay, very important. And so if you can do that, that was all that was expected from you for question 6.1.1. Now let's go to question 6.1.2. Here again, you have ft that is given to you like this, and you need to be able to look at your table and identify a function that closely resembles this function here. And so if we do that, you will find then that in row 9b, you have this function here, which is a function in the time domain that closely resembles this function here. But now you need to use your intelligence here, because somebody else may say, but when I look at this function in the table, it's got e to the power of minus at minus e to the power of minus bt. But here what I have is 1. I do not have e here. Well, the reason you have 1 is because if you have e to the power of 0, that of course will give you 1. And so you can already tell therefore that the value for a is actually 0. Because if you do e to the power of minus 0t, it's e to the power of 0, and so that's 1. Okay, that's why you have 1. So the value for a in this case is actually 0. And so if a is 0, then what is the value for b? The value for b is 5, because if you look at this here, you will see that it's e to the power of minus bt, and here we have e to the power of minus 5t. So b is 5. Okay, and then capital A, of course, as you can see for yourself, capital A is 60. And so once we have established that, then we have this like that. Capital A is 60, small a is 0, and small b is 5. Once you have these, then writing the writing the Laplace transform in the S domain, you will just take this expression here and replace the constants by their value. And so if you do that, then you have Fs will be equal to 60 divided by S plus A. A is 0, so that's just S, and then multiplied by S plus B. B is 5, so it will be S plus 5. Okay, so that's pretty much all you will have for Fs, question 6.1.2. Now, let's go to question 6.2. We are given this function in the S domain or the Laplace domain, and now we have to find the equivalent in the time domain. And so what we're looking for is Ft. Now, if you look in the table, you will see that in row 21b, you have a function that looks like this in the S domain. And if you look at this and you look at that, you will see that they resemble each other, okay, these two functions. And so you can tell that capital A in this case will be 45. You can tell that small a here is 7 and small b is 5. Okay, you can see that. And so once we have seen it like that, then we are ready to go. Okay, so a is 45, capital A is 45, small a is 7, and small b is 5. And so once we have this, then we can write the function in the time domain. And in this case, you can see it's a very long function, but all you will have to do is just replace capital A by 45 in this expression, small a by 7, and small b by 5. So you replace that into this expression, and so what you will get for Ft will be this, okay, 45 multiplied by all that. Okay, all I did is just replace capital A by 45 and replace small a by 7 and small b by 5. So for instance, here you have small b minus small a. Small b is 5 minus small a is 7. So 5 minus 7, it's minus 2. That's why you see I have minus 2 here. And then multiplied by omega squared plus a squared. A is 7. 7 squared is 49. So that is why I have omega squared plus 49. And you go on doing like that, the same thing, just replacing capital A by 45, small a by 7, and small b by 5 in this expression. And that will give you the time function that you are looking for, okay? So this is what it is here. But in this case, you mustn't stop here, because if you look at your table, you will see that once you have found the time function, you need to specify what the value of phi is, okay? I don't know if, I think this is C, okay? I suspect, okay? So you need to specify what that is, okay? And so you are given also an expression for that, here like that. And so you will just go ahead and plug in the numbers and find the value for this. And again, this expression is also in terms of A and B and so on and so forth. It's not very easy to see what it is here, but you can go in your table and look at the row 21b to be able to see clearly what that is, okay? But here I just plugged in the numbers. And so I also said where, you can see I wrote where, and then I find my value for phi. Phi is equal to tan minus 1 of omega multiplied by a plus b. A is 7, b is 5, a plus b is 12. Omega multiplied therefore by 12 divided by a times b, which is 7 times 5, 35 minus omega squared. Okay, so this is what this is equal to. And so once you have this like that, then of course you also need to add that this value is between 0 and pi. Okay, so you just add that in brackets exactly as you see it done here. Okay, this is between 0 and pi. Okay, like that. And so once you do it like this, you've done everything that was expected from you for this particular question. In this case, for question 6.2, emphasize that if in your table you do have a situation where it tells you where something is equal to something, you also need to add that to your answer. Many students, they will stop here. They will just find ft and they will stop there. But it is not right, because in your expression for ft, you have this value here that needs to be defined. And so in this case, therefore, you need to use that little equation here to define this. Okay, so if you do that, this is what you will get. And of course, you need to specify that this is valid for values between 0 and pi, exactly as you see it done in the table. Okay, this is very, very important. Okay. Now, another example. A system's transfer function is given by this. Okay, so you have the transfer function of a system and it is given by that. And now, if the system is subjected to a unit step input, determine the response yt of the system using Laplace transforms. Okay, so you have the transfer function of a system. This is what you see here. And they tell you if this system is subjected to a unit step input, then what will be the value of yt? Okay, you have to understand that in the time domain, the equivalent of ys is yt, and the equivalent of xs is xt in the time domain. And so in this case, you are told that you have a unit step input, which means that xt is equal to 1, okay, because the input is with x and the output is with y. Okay, so the input is with x and the output is with y. That's how you need to understand it. That is why they say to you, you need to determine the response yt, because yt is how the system will respond to an input xt. Okay, and the input, of course, is a function of time, because at various times you have different inputs. And also, since you have different inputs at various times, therefore the output y will also be a function of time, because at various times you will have different output. Okay, so that's very, very important. In the later modules that we're going to do, you are going to begin to be very familiar with this concept. And so this is the question that we have. So as I was saying, the input is actually xt. Okay, in the time domain, the input is xt. And the input is a function of time, because if you have a specific system, at various times you can send different signals at different times. That is why the input is also a function of time. And because the input is a function of time, the output yt is also a function of time. And so in this case, the input is xt, and you are told that the system is subjected to a unit step input. What that means, it means that xt is equal to 1 unit step input. Okay, so xt is equal to 1. Now that we know that xt is equal to 1, we can find what is xs. Capital XS is the Laplace transform of xt. Okay, and so if we do that, capital XS is the Laplace transform of xt. So xt is 1, so the Laplace transform of 1 is just 1 over s. Okay, very easy. So now we know that xs is equal to 1 over s. Okay, now this transfer function that we have here is this here, but we do know what is the value of xs. Okay, it's 1 over s. So we can rewrite this function like this, okay? We take the xs we send to this side, and then we will replace this xs by its value, 1 over s. And so if we do that, this is what we have, okay? And so we can go a step further and write it like this, okay? Because since we're multiplying by 1 over s, this s might as well come here in the denominator. And so if we do it like that, then this is what we have, okay? So this is what ys is. Why is it important for us to find an expression for ys? It's because in this question, we're trying to determine the response yt. So we have the Laplace transform of yt, which is ys, and now we're going to use our table to go back and find the equivalent in the time domain. Okay, so we do have ys, so we need to find yt. But as it turns out, in this case, this ys is not easy to find. In fact, you will not find it in the table. You do not have an expression like this in the table. So what that means, it means that you need to simplify this expression until you get an expression that looks like something in the table. But from this here like this, it's not easy for you to see anything similar to this in the table. So for us to be able to transform this into a simple expression that we will be able to recognize from the table, what we will need to do is to split this expression into a product of simple terms, okay? So like for instance, if you look here, you can see that you have s multiplied by s squared plus 6s plus 8, okay? Somebody may be tempted to say, okay, let me take this s and multiply into this bracket. That will be a mistake because you will make the expression look more complicated than it already is. The idea is to try and simplify this expression in such a way that we can read the table and find things that look very similar to what we have, okay? And so we're not trying to make it more complicated, but we're trying to simplify it. And so if you remember from your math course, if you have s squared plus 6s plus 8, this can actually be written into a product of s plus 2 multiplied by s plus 4. Okay, as you can see here, s squared plus 6s plus 8 is equal to s plus 2 multiplied by s plus 4. Okay, this is from maths. Okay, it's elementary. You should be able to break this into this multiplication. Okay, so you can see already that things are beginning to look a lot simpler than what we had here. Okay, so therefore we will break this into these. Okay, and so if we do that, this is what we have. So you can see now that ys is equal to 4s squared plus 22s plus 40 divided by s multiplied by s plus 2 multiplied by s plus 4. This is just that. We replaced it by that because this is equal to that. Okay, once you have it like this, you will again remember from your maths course that it is possible, if you have an expression like that, to write it like that, okay? And so ys is actually equal to a over s plus b over s plus 2 plus c over s plus 4. So this here can be written like that, but what we now need to do is to find what is the value for a, for B, and for C. And so for us to be able to do that, we are going to put everything here under the same denominator. And then once we do that, then what we will have in s squared must be equal to 4. And what we will have in s must be equal to 22. And the rest must be equal to 40. Okay? So this expression like this can be rewritten as something like that. Okay? And of course, in this case, now we have to find the values for A, for B, and for C. If we rewrite it like this, what A is, what B is, and what C is. So that's what we're trying to find. But to be able to do that, as I said, we will again put them all under the same denominator. And so if you do that, you have it all under the same denominator. This is what you will get. And then from here, you can then work out the numerator and then group the terms. So the terms in s squared, you will put them together. The terms in s, you will put them together. And the terms that are just neutral, you will leave them also together, okay? And so if you do this here in the numerator, what you will get then, it's something like that. And again, I am not gonna get into much of the details here because this is elementary maths. You're supposed to be able to do that. I am assuming that you know how to do that. And so once you have it like that, you can see now we have this in s squared, we have that in s, and we have this term here that is just the neutral term. And so since this here is equal to that, then we can say that a plus b plus c must be equal to 4 because it's 4s squared. 6a plus 4b plus 2c must be equal to 22. And then 8a must be equal to 40. Okay, so if we do it like that, then that is what we get. And so from this here, you can then find the value of a, b, and c. In fact, from the third equality here, it's easy to see that a will be equal to 40 divided by 8. So a is already 5. And so you can replace that into these two equations on top and then solve for B and C. Again, I am not going to go in the details of doing that. You can do it for yourself as an exercise. But here I am just going to give you the solution to this. Okay, so A is equal to 5. Okay, if you solve these three equations, you will find that A is equal to 5, B is equal to -3, and C is equal to 2. Now that we have A, B, and C, we can now write Y, S here and replace A, B, and C by their values. Okay, so if we do that, this is what we get. And this ys that you have here, if you put it all under the same denominator, you will end up with this expression. But why is it that it was important for us to write to simplify this expression and turn it into that? It's because with this here, it's very easy to find the function yt in the time domain. With that here, it's really difficult because nowhere in the table you find an expression that looks like this. But if you look at this, in the table, you can easily find an expression that looks like that, and then one that looks like this, and then one that looks like that. And so it becomes very easy for you to work it out, okay? And so this is what we have for our ys. Now we need to find yt because the question is asking us to determine the response yt. And so for that, if we look in our table, what we find, okay, of course, we're trying to find yt. So in our table, what we find is that if you have a function in the S domain that looks like that, which is the case with this and this, and even that, okay, because in this case here, A is just 0, okay, you can see that. Here, if you look at this, A is 0, okay, and so these, therefore, in the time domain, give you a function looking like that. Okay, so if we look at the first one is 5 over s. Okay, so we look at this. So of course, capital A will be 5. Okay, and small a in this case will be 0 because we just have s at the bottom. So capital A is 5, small a is 0. So e to the power of -0t, so that's 1. So therefore, here for this one, if we take it to the time domain, this is just 5. If we look at the second one in the middle here, capital A is 3, small a is 2. So therefore, in the time domain, this one will be 3e to the power of -2t, okay? So it's going to be 5 minus 3 e to the power of minus 2t. If you look at this one here, capital A is 2 and small a is 4. So in the time domain, this term will be 2 e to the power of minus 4t, okay? And so if you understand that, then you can quickly write yt like that, okay? And this is what you will get for yt. And why is it that we have a negative sign here and even here? It's because the value that we had for b was minus 3, okay? So we just put the minus sign there, okay? And so if you take this expression and transform it back to the time domain, because here it is in the S domain, then this is what you will get. And you can easily find this by just looking at the row 8b in your Laplace transform tables, okay? Very, very important. And so it's quite important for you to be able to use that table. Otherwise, you will struggle a lot with this module. That's all from me today. I hope this presentation was helpful to you. If you wish to get in touch with me, feel free to use the number in the description. The notes that I used in this presentation are available upon request. I hope this was very, very helpful. Thank you so much.